This is an example of the problems at level 4, or the mastery level, of the Laplace Transforms game in Circuit Tutor. As always, we have examples available at a variety of levels here, and it would be a great idea to view some of these. So I'll show you just one example. And so that shows you all the steps involved in doing the problem. So if you have any questions about doing these problems, it would be recommended to view those. There's also user-selected examples available here. If you want to look at a problem of a particular type, you can select the particular function and view a problem of that specified type, optionally with time shifting if you click this box. Okay, so let's go back and do the mastery level problems. So in this first problem, I'm being given a function of time, which involves a sum of 3 different terms. So I remember from the Laplace transform properties, which you can review here if necessary, that Laplace transforms are linear, which is based on the fact that Laplace transform is defined as an integral of this function, and integration is a linear operation, as you know. Therefore, the Laplace transform of the sum of 3 functions is the sum of the Laplace transform of each term taken individually. Therefore, I just need to do those 3 and add them together. Now, in order to have the table available, I could open it up here, which will just open it typically as a new tab in my browser by default normally. Since that's not real convenient, if I want to see that at the same time as the problem, I'm instead here going to open that by right-clicking and select Open Link in New Window, which will open a different browser window, which I can then reduce the size of that and place it side by side with the problem window, and that'll allow me to use the table and at the same time that I'm working the problem. Okay, so let's look at the first term. We have basically a constant, negative 11 times t cubed e to the negative 7t u of t. So that's a product of a polynomial and an exponential, decaying exponential function with the unit step function, as is always present. So look at that, and that corresponds to this entry in the table. So in this case, I have t cubed, so that corresponds to n equals 3. So I need 3 factorial, and remember factorial is just the product of the integer with all smaller integers down to 1. So it'll be 3 times 2 times 1, or 6. And then in the denominator, I'm going to have s plus a, where a is the decay constant of the exponential, the coefficient of the t, raised, in this case, to the power 3 plus 1, or 4. So the first term here. And also I need to notice that in this equation entry system, I have 3 different tabs of palettes of terms that I could use. And since I'm trying to enter a Laplace transform in the S domain, none of these terms will be relevant. These are all in the time domain, as indicated obviously by the fact that they have the time variable here. And likewise, this tab will not be useful either because that's time-shifted terms. So I need to be in the Laplace domain always to enter a Laplace transform. And notice that all these terms are functions of the variable s, the Laplace transform variable, as they should be. Okay, so then to enter that first term, I will need a ratio. So I'll enter a fraction term first. And just anticipating a little bit more, I'll need another ratio for this term. So I'm going to plus sign, and then another ratio. And then I'll need another term, which will actually just be a constant term there. So I'm just going to go plus and a constant. And then I'll fill all that in as we go along here. Okay, so for the first term, I have that constant in the numerator. So let's put a constant there. And then I need the s plus a power in the denominator. So I'll put that there. And remember that because the n was equal to 3, that I'm going to have that raised to the 4th power. And then the a value, in this case, it's negative 7t, so my a will be 7, based on the formula. And then I have the n factorial, the 6, but that multiplies the negative 11, so I'm going to have negative 66 here. Okay, then for the second term, this is simpler. It's just 10 u of t, so for the unit step function, I can hopefully remember that the Laplace transform of that is just 1 over s. If you need to, you can look it up in the table. But these first 3 entries I would certainly recommend you memorize, as they are used very, very frequently. So that'll just be 10 over s. So I'll bring in a k term and an s term there, set that exponent equal to 1. And then my k here will be that 10. And then the third term is minus 8 delta of t, where that's the unit impulse function, or the Dirac delta function, as it's also known. And again, that's one that we should have memorized. The Laplace transform of that is simply 1, as indicated in the table. So this will just be a negative 8. So I could have put a negative sign here, or I could just put it in the value here, which I'll do for convenience there. So we'll check that. And that is correct. Okay, and then you always have the option, if you were unsure about any of this, to view a detailed solution here, which will be similar to what you saw in the example. And it'll just take you through all the details of computing the answer. Okay, so let's do a second problem at the mastery level, which will be a little bit different type of problem. So in this case, I see that I have a negative 6 e to the negative 10 times the quantity t minus 11 times the unit step function with an argument of t minus 11. So what I may recognize here is that this is a time-shifted function. Therefore, it will be useful to use the time-shifting property of Laplace transforms in solving this. I could, of course, make the e to the basically 110 here and make that a coefficient and put that in the constant out front, but that would actually be self-defeating because it's easier to do this with everything inside the, that is, everything time-shifted in terms of the argument. So if we remember the Laplace transform properties, we'll use the time-shifting property, which is shown here. And remember that if both the function and the unit step function are both shifted by an amount t minus t naught, in other words, the function turns on by the unit step function at a time t naught, and the entire function has been shifted, then that simply introduces an exponential factor in front, which is e to the negative t naught s, where the t naught there is the amount of time shift. There's another alternative form if only one of the two things was shifted, the unit step function, but this is the one that's going to be relevant here. So I just need to put in that exponential term in front of the regular problem. So, and then of course the basic function here is just the exponential times the unit step function. Of course, that's one that we typically have memorized. That would be this function. So I'm going to start out, of course, going into the Laplace domain, as always. I'm going to put in my exponential function first, and then I'm going to put in a fraction term after that, since I need to have those two multiplied. So I can just click on those to move them in. And again, if you ever decide you need to remove a term, just drag this out of the equation entry area here, and it'll be removed. Okay, so the time shifting, I may as well start with that. It's shifted by an amount of 11 seconds, and so that will be e to the negative 11s. So I just put that number in there. And then now the function that I'm shifting is basically the negative 6 times the decaying exponential. And so I'll need a constant in the numerator, which will be my negative 6, which is the coefficient here. And then it's just 1 over s plus a. So I need an s plus a term in the denominator. And the a here will be the coefficient of the t minus 11, which now we're thinking of that as t basically because we're already applied the time shifting property. So that will be a will be equal to 10 in this case. And that should be the answer. So let's check that. And that is correct. And once again, we do have the option for a detailed solution if there's a need for that. Okay, so let's continue. And now we'll do the third problem at the mastery level, which again will be a little bit different type. So once again, we can see that this problem involves time shifting. Here we've shifted both the cosine function and the unit step function by an amount of 6 seconds. The units are not indicated there, but those are understood, if not otherwise indicated, to be seconds. So that means we'll again need the exponential factor. So I'm going to go into Laplace domain, as always, start with my exponential factor. And that'll take care of the time shifting. And if I like, I can put in the value that's going to be 6 seconds. So I'll just put in a 6 there. Then I need to look up the Laplace transform of the cosine function, because that's the basic function here. And that's just this s divided by s squared plus omega squared. So I'll need a fraction term for the cosine. And I'll need the s squared over s squared plus omega squared, but I'm also going to need a constant because of the constant out front here. And then I need the s term, which I'll put next to that. And that'll be s to the 1. And my constant here will just be the 6. And then in the denominator, I need the s squared plus omega squared, and that term is available here. And the omega here will be the coefficient of the, in this case, t minus 6 in the cosine. So that will be the 2, and I need to square that here. So that will be 2 squared, or 4. So that should complete that answer. And so we'll check that. And that is correct. Okay, and again, detailed solution is available if you need that. So let's then do the last problem on the mastery level. And this time, we see that we have something a little bit more complicated. Now we have a constant times a decaying exponential that has been time shifted by 10 seconds. And then there's also a factor of a sine function, which has also been shifted by 10 seconds, and the unit step function. So again, you see everything here has been shifted by 10 seconds. So once again, we need to go into the Laplace domain and use the exponential factor to accomplish the time shifting. So that'll be a shift of 10 seconds. So I'll place that there. And then I need the transform of the decaying exponential times a sine function times u of t. And so I need to scroll down here a little bit in my table, and that will be this entry here. And so you see I need an omega in the numerator and this expression in the denominator. So let's put in a fraction here. And so the omega in the numerator, that will just be a constant basically. And the omega here is going to be the argument inside the sine. That's the multiplier of the t minus 10. Of course, that's the definition of omega here. I'm sorry, in this expression here, it's not phase shifted in this case. And notice I don't really want to use the phase shifted formula for sine here, because that would then not make it time shifted like the other terms. And so it's much easier to use the time shifting property in all three of those terms than it is to treat this as a phase shift, even though you could say that that's a phase shift of 30 radians, but that's not the best way to treat this. So again, I need an omega in the numerator, so that's going to be this 3 here that multiplies the t minus 10 in the assigned argument. So I have the 3, but I also need the prefactor of 10, so that's going to be a constant of 30, the 3 times 10. And then in the denominator, now I need the s plus a quantity squared. So I'll use this type of term there, and then put in exponent squared there. And then I'm going to need a plus, and then another constant here for the omega squared. Oops, down there. And then the a here is going to be the coefficient of the t minus 10 and the negative sign, so that's going to be the 12. So it's the s plus a quantity squared, which is again here, and then the omega squared, again that's the 3, and that needs to be squared, so now 3 squared, of course, is 9. So that should complete the entry of that problem, and that is correct. And then once again, we do have the option to view a detailed solution if you wish to do that. So that does complete the mastery level, and that is the end of this example.